To ensure the safety and reliability of a structural member, it is necessary to restrict the applied load to one that is less than the load the member can fully support. There are many reasons to do so to restrict the applied load, in addition to the obvious reason that we should never exceed the capacity of the member. There is inherent uncertainty in how a structure may be loaded and how the material will perform. For instance, the measurements of a structure or machine may not be exact. Unknown vibrations, impact, or accidental loadings can occur. Atmospheric corrosion, decay, or weathering can cause materials to deteriorate over time, and some materials show high variability in mechanical properties. Design codes, which are legally binding codes of reference, specify rules, standards, and safety factors regarding the design and construction of structures and machines. Here's a summary of the engineering design philosophies: ASD, Allowable Stress Design, and LRFD, Load and Resistance Factor Design, also known as Limit State Design. ASD was the first organized method used to safely design and build structures. It is a relatively simple concept based on factors of safety and straightforward to understand. LRFD was developed more recently in the 1950s to 1970s. It's a less simple method, but more comprehensive, and it is based on two types of factors, which are load factors and resistance factors. As mentioned, allowable stress design is based on factors of safety that we can abbreviate as F period S period. The greater the factor of safety, the safer or more conservative the design. To learn about this design method, consider the definition of factor of safety. FS, factor of safety, is the ratio of two things, F sub fail over F sub allow. So F fail is the failure load, which is the force at failure of the member. That's determined through experimental testing. F allow is the allowable load, the maximum force that is allowed to be applied to the member while in actual operation. Based on this definition, we see that the factor of safety is a unitless quantity, as it is the ratio of two forces. We can also see that because we require F allowable to be less than F failure, meaning we never want to exceed the failure load, values of factor of safety are never smaller than 1, always greater than 1. A greater factor of safety implies a safer and more conservative design, whereas a lower factor of safety indicates a less conservative but more cost-efficient design. Factors of safety vary for different applications and materials, depending on the level of variability or uncertainty of loading scenarios and material reliability. Common values of factor of safety are between 2 and 3. Factors of safety can also be defined or expressed in terms of stresses, where we can have factor of safety equals sigma fail over sigma allow in terms of normal stresses, or factor of safety equals tau fail over tau allow in terms of shear stresses. In summary, allowable stress design is based on factors of safety that are always greater than 1. If we are given values of factor of safety and sigma fail, the failure stress for instance, then sigma allow, the allowable stress, can be calculated. And in turn, we can calculate the required size or cross-sectional area of a structural member that is subjected to a known load. A more recently developed design method called load and resistance factor design, or limit state design, involves the use of two different types of design factors, load factors and resistance factors, also called strength factors. Unlike ASD, LRFD separates the uncertainty of loadings from the uncertainty of material strength, which can lead to a more efficiently designed structure. The general LRFD design criterion is as follows, so it is an inequality here. This side must be greater than or equal to this side, where we have phi p sub n is greater than or equal to the summation of gamma I ri. The left-hand side, which is phi p sub n, represents the factored strength of the member. And the right-hand side, summation gamma I ri, represents the sum of factored loads to be applied to the member. The sum of factored loads, of course, must never exceed the factored strength of the member. Each quantity above is defined as follows. P sub n is the nominal or theoretical strength of the material, the load that causes failure. Phi, the Greek letter phi, is the resistance or strength factor. Phi is generally less than 1, such that phi p sub n is less than p sub n, so the factored strength is less than the nominal or theoretical strength. R sub I is the applied or anticipated load. Gamma sub I is the load factor, which is generally greater than 1, such that gamma R for any given load is greater than R. In other words, we can consider the left-hand side to be an underestimation of the capacity or strength of the material, and the right-hand side to be an overestimation of the loads that may be applied to the member.